Welcome back. Today we will see programmable logic devices. The mux will continue after this video. Okay. Now if you observe that PLDs, programmable logic devices, are mainly categorized into three types: PROM, PIL and PLA. PROM stands for programmable read-only memory, PAL stands for programmable array logic, and PLA stands for programmable logic array. We will see the comparison of these three PLDs. Okay. Yeah, we will see the comparison between PIL and PROM and PLA. If you observe that here, okay, in PROM it consists of unplane and also R plane. Similarly, in PIL also it consists of underplane and also R plane. In PLA also underplane and R plane. But very important point is the second point. If you observe that in the second point, okay, that is very important point. If you observe, okay, in this second point, okay, fixed underplane is going to be used. That means a fixed underplane, programmable R plane. Fixed underplane means decoder. But in PAL, if you observe that programmable underplane, if you observe that in PAL, programmable underplane, okay, but fixed R plane. Now in PLA, both are programmable. That is very important point. If you observe the block diagram of it, okay, in PROM, underplane is fixed, R plane is programmable. In PAL, underplane is programmable, R plane is fixed. Now, whereas in PLA, if you observe that programmable underplane, programmable R plane, but very important point is the output of R plane is not taken directly. It is taken with the help of an XOR gates. Okay, that is very important point. Is it clear? Remember this very important point. Okay, the output of R plane is not considered directly, it is going to be considered with the help of an XOR gate. Now we will see the implementations step by step. I will start with the PROM. Now if you observe in PROM, what are the steps I am going to use in programmable read-only memory? If you observe that, we have to obtain the sum of minterms from the question, and also we have to decide the decoder. That means we have to decide the size of the decoder. That is a very important point here, and after that we have to decide it. Okay, now we will see some of the examples based on this. Is it clear? Now observe the question carefully. What is the question given? Implement full adder using PROM. That is the question given. If you observe that, here we have to obtain the sum of minterms from the question. What is the question given? We have to implement full adder. Now we know that full adder consists of three inputs. If you observe that full adder consists of three inputs, let us consider A, B, C are the inputs, sum and carry are the outputs. Now we know that since we are having three inputs, we can able to form 8 combinations. If you observe that, I am going to write the 8 combinations here. Now if you observe the truth table of it, okay, this is the truth table of full adder. Now I am going to write the boolean expressions, that means sum of minterms for the two outputs, that is, okay, sum and carry. Now at what positions sum is going to be active? At 1, 2, 4, 7 position. Therefore I can able to write 1 comma 2 comma 4 comma 7. Now similarly for carry, if you observe that at carry, what is the position we are having? If you observe that 3 comma 5 comma 6 comma 7, that means 3 comma 5 comma 6 comma 7. This is the first step we have to do. Okay, we have obtained the sum of minterms here. Then we have to decide the decoder. What is the size of decoder means? Since if you observe that what is the highest digit here, 7 is the highest digit, therefore definitely we require 3 to 8 decoder. Is it clear? Therefore we have to use 3 to 8 decoder here. Is it okay? Now we will see the design it. Now if you observe that we have to use a 3 to 8 decoder here. I'm going to use a 3 to 8 decoder. If you observe very carefully, I'm going to use a 3 to 8 decoder. Okay, I'm going to draw a 3 to 8 decoder. If you observe, I'm going to use here three inputs: A, B, C are the inputs. Since these are the inputs for full adder, if you observe that A, B, C are the inputs. Now since it is about 3 to 8 decoder, it is 3 to 8 decoder. Now how many outputs we are having? 8 outputs: 0, 1, 2, 3, 4, 5, 6. Sorry for that. Okay, 6 and finally what? 7. 6 and 7. Now if you observe that I'm having fixed AND gates with the help of decoder. Since it is a PROM implementation, I'm having fixed, okay, AND gates with the help of decoder here. Now how many output functions we are having? Two output functions, therefore we can have two OR planes. Now if you observe that this is my OR gate, and this is my programmable OR gate. Now let us consider it is sum, it is carry. Now what should we have to do means we have to give the fuse contacts here. If you observe the fuse contacts, how I am going to give. Now if you observe that sum is 1, 2, 4, 7, therefore I will give the fuse contacts 1, 2, 4 and finally 7. Now if you observe that 3, 5, 6, 7, now I am going to give for 3, okay, 5 and 6 and 7. Okay, this is the implementation of full adder using PROM. This is the way you have to implement using PROM or using ROM. Okay, using PROM or ROM. What is the size of this means? What is the size of this means? If they talk about size, the size is 8 by 2 ROM. The size is 8 by 2 ROM, where the 8 is nothing but the outputs of decoder, the 2 is nothing but the output functions, sum and carry. Is it clear? Now we will see some of the example here of the. Now if you observe that if they ask to design 32 by 4 ROM, if they ask to design 32 by 4 ROM, now if you observe that, if you observe very clearly that where 32 is nothing but what output of decoder, that means we require what 5 to 32 decoder. That means I have to design 5 to 32 decoder. 1, 2, 3, 4, 5 inputs. This is 5 to 32 decoder. Okay, now I can able to have 32 output 0, 1, 2 and so on. Finally I can have 31. Now 0, 1, 2 and so on. I can have 31. Now how many OR functions I require? 4 OR functions. That means I require programmable OR gates 1. Okay, this becomes 2. Okay, this becomes 3 and sorry for that, and finally if you observe that this becomes 4. Okay, in this way you have to design, okay, the size of ROM. Are you clear? Now we will see some more example based on the PROM. Is it okay? Now if you observe that what is the question given here, if you observe what is the question given, okay, we have to implement the following boolean functions using PROM. Now if you observe that all these three functions are directly given in the form of sum of minterms, okay, are directly given in the form of sum of minterms. Now what is the next step we have to do? We have to decide the decoder. If you observe that each and every input function, what in the each and every output function, sorry, okay, how many input variables they have specified? 3 input variables. Therefore we require 3 to 8 decoder. Otherwise you can able to check what is the highest digit. 7 is the highest digit, therefore you can able to design 3 to 8 decoder. Okay, therefore I am going to use 3 to 8 decoder here. If you observe that I am going to use the 3 to 8 decoder, observe very carefully how I'm going to use a 3 to 8 decoder. If you observe very carefully, okay, now I'm going to draw this implementation. Sorry for the inconvenience. Now I required one 3 to 8 decoder. What are the inputs they have given? A, B, C are the inputs they have given. 3, sorry, okay, 3 to 8 decoder. 3 to 8 decoder. Now if you observe that 0, 1, 2, 3, 4, 5, 6 and 7. Okay, now this is the size here, the 3 to 8 decoder. Now if you observe that I'm going to extend the output lines here. Now if you observe that how many output functions are there? 3 output functions are there. Therefore I required 3 programmable OR gates. This is 1 for F1, this is another one for F2, and this is another one for F3. I will write this as F1, F2, F3. Now I will give the fuse contacts. If you observe that I am going to give the fuse contacts here. It is 0, 1, 3, 5, 0, 1, 3, 5. Now if you observe the second one, what is that? 1, 3, 5, 7. 1, 3, 5 and 7. Now what is F3? 0, 2, 4 and finally it is 7. That's it guys. In this way you have to design or implement the following boolean function using PROM. Okay, in PROM if there is f4, sorry, if there is f4, f5, f6 and so on, whatever it may be, f5 and so on, just you have to draw one more OR gate here. Okay, one more OR gate, you have to give the fuse context. Are you clear? This is the PROM implementation. Okay, if you are having any doubt in the PROM, you can able to please comment it. Okay, now next we will see one more programmable logic devices, that is PAL. Is it clear? Now let us come back. If you observe that we are going to see programmable array logic. In this programmable array logic, the first step is you have to obtain the simplified Boolean expression using Karnaugh map. If they have given directly in the question, use it. Okay, not necessary to do the K-map if they given directly in the question. The second step is we have to fix the OR array by observing the product terms in each and every output function. Okay, then very important step is we have to write the programming table. That is a very important step. After that we have to design it. Is it clear? Now we will see an example here. Now if you observe that the question given here, okay, we have to implement the following boolean function using PAL. In that function they have given f1 of a comma b comma c is equal to summation m of 1 2 3 7, f2 of a b c is equal to summation m of 3 comma 6. If you observe that the boolean expression is not given directly, therefore I have to do k-map to obtain the simplified boolean expression for f1. Okay, since if you observe that I'm having, okay, three input variables, therefore I require three variable k-map here. Now I'm going to plot, sorry for that, I'm going to plot three variable k-map. If you observe that I'm going to plot the three variable k-map. Okay, since three variable, how many cells it contains? 8 cells it contains. Now let us consider a b c. Okay, this is 0, this is 1, this is 0. Sorry for that, I will write all this. If you observe that, now if you observe that I have written that three variable k-map. Now I'm going to substitute in the positions of 1 2 3 7. This is one position, okay, this is two position, this is three position, and this is seventh position. Now if you observe that I can able to group like this, one pair, okay, another pair, and one more thing I can able to pair like this. Therefore I can able to write the boolean expression from this a complement into c plus, from the other pair it is also what, a complement, sorry for that. Okay, a complement, if you observe that it is a complement into which one is common in the second one, b is common, plus now it is bc. This is the boolean expression for f1. Similarly the boolean expression for f2. Now if you observe that I'm going to obtain the boolean expression for the second function, that is f2. What is the position of f2? 3 comma 6, 0 1 2, this is 3 4 5, this is 6. If you observe that it is having isolated ones. Okay, now if you observe that what is the boolean expression means, f2 becomes a complement into bc plus, sorry, a into bc, not a complement, this is a into bc. If you observe that a into bc, okay, sorry, a complement into bc, yeah, absolutely right, it is a complement into bc plus a into b into c complement. Now these are the boolean expressions. Now this is the first step. Now if you observe that we have to observe the output functions, each and every output functions. Here if you observe how many product terms are there, 1 2 3, but here how many product terms are there, 1 and 2. What is the maximum product term count? 3 is the maximum product term count. 3 is the maximum product term counts. Therefore we have to fix for each and every OR gate 3 product terms. We have to fix 3 product terms. But if you observe that in this f2 we are having only 2 product terms, therefore we have to use one unused product term, one unused, okay, product term. Now we will write the programming table here. How to write a programming table? If you observe that, okay, how to write a program. Now if you observe that in step 2 we have to write the programming table. That is a very important step. Okay, the first column should be product terms. Okay, the first column should be product terms. Now the second column should be inputs. The second column should be inputs. How many inputs it contains? 3 inputs, a b c. Okay, the third column should be outputs. The third column should be outputs. Now here don't write the outputs here directly. Now if you observe that, how many product terms we are fixing that? In each and every output functions, 3 product terms. That means 1, 2, 3. The first 3 product terms is fixed for F1, which is equal to A complement into C plus A complement into B plus BC. The remaining fourth, fifth one and sixth one is fixed for F2 here. F2 here, if you observe that A bar B into C plus we are having A B C bar. That means one unused one is there. Okay, we will see how to fill this table. Now what is the first product term? If you observe, this is the first product term, that is A complement into C. Here A complement means 0, B is not used, C as it is 1. Now what is the second product term? If you observe that A complement into B, A complement into B. Now A is 0 once again, B is 1, C is not used. Now what is the third product term? If you observe that B into C is the third product term, A is not used, B is 1, C is 1. Now if you observe, what is the fourth product term? A complement B into C. Now if you observe that this is A complement B C, what is the fifth product term you are having? A B C complement. That means A B C complement is 0. Now there is no sixth product term here, therefore you have to left this and you have to write unused one like this. In this way you have to fill the programming table of it. Now based on the programming table we can able to draw its structure. If you observe that I am going to draw the structure, since I am having 3 inputs, I can able to draw A complement, B B complement, sorry for that, B complement, similarly C complement. Now how many product terms we are having? 6 product terms we are having. Therefore I will use a different color for representing 6 product terms. That means 6 AND gates are required. 1, sorry for that guys. Okay, I will finish the 6 AND terms here, 6 AND gates. Now if you observe that 6 product terms we are having, since 6 product terms, okay, therefore I have drawn 6 AND gates. Now how many output functions we are having? 1 and 2. Therefore we have to draw 2 OR gates here, 2 OR functions. This is 1 and this is 2. Let us consider F1 and F2. Sorry for that guys, once again sorry for the inconvenience. Okay, this is F2. Now if you observe that the first 3 product terms should connect to F1, 1, 2, 3. The next 3 product terms should connect to F2, 1, 2, 3. Now if you observe that in F1, oh sorry, in first product term, what is the connection? A complement into C. Okay, for second product term, A bar into B. That means once again A complement into B. The third one is B into C. That means B into C. What is the fourth one? A complement into, now if you observe that A complement into B into C. Okay, now what is the fifth one? A into B into C complement. A into, okay, if you observe that B into, now if you observe that C complement, sorry for that, okay, sorry for that, C complement. If you observe that A into B into C complement. Now what is the last one? If you observe that, okay, it is an unused one. If you observe that it is an unused AND gate, therefore inside of AND gate you have to use a cross mark. Okay, this is the implementation of PAL. Okay, once again I am telling that first of all you have to obtain the simplified Boolean expression and you have to observe each and every minterm, sorry, each and every product term you have to take the maximum count. Okay, here in F1 we are having 3 are the maximum count, in F2 we are having only 2. Therefore what is the maximum count? 3 is the maximum count. I am going to fix that. Okay, therefore if you observe that 1, 2 and 3, okay, 1, 2 and 3, I'm going to fix for each and output function 3 product terms. Therefore overall I am having 6 product terms. The first 3 product terms are present in F1. Okay, that's why F1. The Next, three product terms should present in F2, but unfortunately one product term is not there. Therefore, here if you observe that one product term is not there, therefore it is an unused one. If you observe that, okay. Now in this structure you have to use, okay. If you observe that here it is a programmable AND gate. If you observe that one AND gate consists of only two inputs, okay. Another AND gate, if you observe that one AND gate consists of only two inputs here, 1, 2, okay. Now some AND gates consist of three inputs, therefore it is a programmable AND. But if you observe that fixed OR gates 3 and 3, in this way we have to implement PAL. Are you clear? Okay, next we will see the last one, that is called programmable logic array. Okay, if you have any query in PAL you can able to ask, please. Now if you observe that we will see the last programmable logic device, that is called PLA. Okay, now before going to solve this question, okay, we will see the steps. We have to observe, is there any restriction in the question, like 3 by 4 by 2, where the first one represent inputs, the second one represent product terms, the last one represents outputs. Okay, obtain the true and, if you observe that the true and complement boolean functions, if there is any restriction, that is very important. If there is restriction, then we have to obtain both true and complement boolean functions. If there is no restriction, we should not bother about complement. Okay, if there is a restriction, we should match the product terms. If there is no restriction, we should not bother about this also. Okay, now after that we have to draw the programming table, we have to write its programming table, finally design. Once again I am repeating that. Okay, is there any restriction in the question like this? Okay, now we have to obtain the boolean functions for both true form and complement form, and we have to match the product terms if there is a restriction. If there is no restriction, no need of complement boolean function and no need of matching the product terms. Directly we can able to write the programming table and we can able to design it. Is it clear? Before that I want to discuss one logic here, very important point I have to discuss here. Now if you observe that in your exclusive OR gate, let us consider, if one of the input is 0, another input is A. If one of the input is 0, what is an output means A itself. If one of the input is 1, then what is an output means A complement is an output. Now that is very important point. If it is 0, one of the input, now whatever may be the other input, it will come as an output. Okay, if one is one of the input, then the output will be the complement of the other input, like this. Is it clear? Now we will see directly the question given. Okay, now if you observe that, what is the question given? If you observe that, okay, we have to implement the following boolean function. F1 of a comma b comma c is equal to 3 5 6 7. Now f2 of a comma b comma c is equal to 0 2 4 7. Of size they have given 3 by 4 by 2. That means three inputs, they have already given that. Two outputs, they already given that, f1 and f2. And what is that, we have to match how many product terms? 4 product terms. That means there is a restriction, therefore we have to obtain true form and complement form boolean function, and we have to match the product terms. We will see how we are going to do this example. Is it clear? Okay, now we will see. Now if you observe that, what should we have to do means, we have to obtain the boolean functions in true and complement form. First of all, I am going to consider the boolean function for f1. Okay, now if you observe that, since I am having three variable, I can able to consider three variable k-map here. I can able to consider three variable k-map. If you observe that, I can able to consider three variable k-map. Sorry for that, guys. Okay, sorry for that, three variable k-map. Now if you observe that, since it is a three variable k-map, how many cells I can able to obtain? 8 cells. Let us consider it is A, this is B, C. Now it will be 0 1, it will be 0 0 0 1. Yeah, sorry, once again. Okay, I'm having this problem. 0 1 1 1 1 0. Now if you observe that, we have to plot for f1 3 5 6 7 position. This is 0 1, this is 2, this is 3. Okay, this is third position. If you observe that, this is the third position. Now after that 5, this is the fifth position, this is the sixth position, and this is the seventh position. Is it clear? Okay, once again if you observe that, this is the third position, fifth position, sixth position, seventh position. Now I'm going to group them. Observe very carefully. I'm going to group them. How I can able to group? This is one group. Yeah, it is disturbing, sorry for that. Okay, first of all I will group them. Observe very carefully. Okay, this is one group. If you observe that, this is one group, this is another group, and this is another group. Now if you observe that, since, okay, I'm grouping with the given data, therefore I can able to say it is f1 in true form. Okay, what is an output means boolean expression a into, if you observe that which one is common means c is common, plus once again a into which one is common means b is common, plus bc. Okay, now I will consider f1 in complement form. In complement form means you have to consider the remaining terms. That means this will be 0, this will be 0, this will be 0, and this will be 0. Now if you observe that, how can we have to do means, okay, we can able to form, sorry for that, I can able to form, I will use different color for that. Once again I will use a black color for you. Okay, I can able to form this one group, two, and this one as. Okay, now if you observe that in the complement form, I can able to write a complement, b complement, c complement, sorry, a complement into b complement, a complement into b complement. Okay, for the first group, plus now after that if you observe that I can able to have b complement into c complement, and plus if you observe that I can able to have a complement into which one is common in these two, c complement is common. In this way I can able to obtain true form and complement form, because they have given the restriction of 3 by 4 by 2. I have to match how many product terms? 4 product terms. Now let us consider a Karnaugh map for f2 here. Let us consider a Karnaugh map for f2 here. Now if you observe that I'm going to draw a Karnaugh map. Okay, now if you observe that I'm going to draw a Karnaugh map for f2, 1 2 3. Okay, now if you observe that a b c, now 0 1 0 0 0 1 1 1 1 0. Now if you observe what are the positions they have given, 0, this is 1, this is 2, this is 4 5 6, this is 7. Now if you observe that how many groups you can able to form, 1 2, and you can observe this is an isolated one. Okay, now I can able to write, since this is the boolean expression for given data, therefore it is a true form. Now if you observe that it is what, b complement c complement, plus, okay, I can able to consider like this, a complement into which one is common, c complement is common, plus if you consider this one, then which one is a into b into c. Now once again I have to consider f2 of complement form, f2 of complement form I have to consider. Now if you observe very clearly, okay, I can able to use different color for you guys. Okay, 0 0 0 0. Now how can I be able to form, I can able to group them, I can able to group them two groups. Now it is what, an isolated one. Now if you observe that I can able to write b complement into c, plus a complement into which one is common, c is common, plus if you observe that an isolated one, a into b into c complement. Now these are the things. Now what is the second step? I have to match the given product terms, the restricted product terms. How many product terms? Okay, 4 product terms. Now if you observe that we are having f1 f2. Okay, I can able to compare like this, true form, true complement form, complement true form, finally complement form. Now in which form I can able to get the 4 product terms? Now if you observe that, okay, true form, okay, is there any common terms here? Okay, there is no common terms. If you observe that in f1 of true form we are having ac plus ab plus bc, here we are having b bar c bar plus a bar c bar plus abc. Therefore from this we can able to form 6 product terms, therefore it doesn't match. Now true and complement form, it is true, it is complement form. If you observe that, is there any matching term? No, once again there is no matching term at all. Therefore here in this form also, how many product terms we are having? 6 product terms, therefore it is not matched. Now I can able to take the complement of f1 and true of this. If you observe that which one is matching, yeah, there is a matching term here. If you observe that b bar c bar is matched, b bar c bar is matched. Now a bar c bar is matched, a bar c bar is matched. Now if you observe that totally the matching terms is going to be take only one time. Okay, this is the first product term, I can able to consider this is second product term, sorry for that. Okay, this is the second product term, I can able to consider this is the second product term. Okay, now this will be the third product term. Now if you come back here, it is already matched, this is already matched, it is already matched. Now what is the remaining one? This one, this is the fourth product term. Therefore how many product terms we are having? 4 product terms, therefore it is matched. no need to check this combination. Therefore we have to consider, okay, f1 complement, f1 complement and f2 in true form, f1 in complement form and f2 in true form. Then we can able to obtain how many product terms? 4 product terms. Is it clear? Now what are the product terms we are having? If you observe that, okay, a bar, b bar, after that we are having b bar, c bar. Now after that we are having a bar, c bar. Okay, now if you observe that, what is the remaining one? abc. abc is the remaining one. Is it clear? These are the 4 product terms. Now we have got this 4 product terms. Now what should we have to do? We have to write its programming table. If you observe that, I am going to write its programming table. Okay, now if you observe that how to write a programming table, the first column should be as usual product terms, the second will be inputs, the third will be outputs. But in the PLA programming table, the outputs are going to be right like this. Now we know that f1 is what form? Complement form. f2 is in what form? True form. Now what is the first product term? If you observe that, a complement, b complement is the first product term, therefore 0 0, it is not used. Now what is the second product term? If you observe that, b complement, c complement is the second product term, a is not used, it is 0, it is 0. Now what is the third product term? If you observe that, a complement, c complement is the third product term, 0, it is not used, it is 0. Now what is the fourth product term? If you observe that, abc is the fourth product term, therefore you have to write a, b, c. Now while filling the output columns, let us carefully observe in f1, okay, in complement form, a bar, b bar, b bar, c bar, a bar, c bar are present. Therefore first 3 are present in f1. Okay, it is not present in f2. Okay, a bar, b bar is not present in true form, the remaining 3 are present. Okay, 1 2 3. In this way you have to fill the programming table. Is it clear? After programming table, what is the next step? Means we have to implement it. Is it clear? After programming table, what is the next step? We have to implement it. If you observe that how to implement, okay, PLA, if you observe that, what is the size they have given? 3 by 4 by 2, that means 3 inputs, a complement, this is what b complement, this is what c complement. Okay, how many product terms? Only 4 product terms, therefore we required what? 1 2 3 4 product terms. Okay, how many output functions we are having? 2 output functions. This is f1, this is for f2. But don't forget, f1 should be in what form? Complement form. Okay, if this is f1, if we want to get a complement form of this, what should we have to do? We have to use an XOR gate here. Now it should be connected directly. Okay, it should be connected directly and the other input should be given as 1. Then it becomes f1 in complement form. Now to get the direct one, that means true form, this is f2. To get a true form, this should be connected as it is and the other input should be given as 0. Now it becomes f2 in true form. Now if you observe that, f1 is connected to first 3 product terms, 1 2 3. I'm observing with this programming table, the last one is not connected. In f2, the first one is not connected, the remaining 3 are connected like this. Okay, now what is the first product term? A bar, b bar, that means a complement, b complement. What is the second product term? B bar, c bar, that means b complement, c complement. What is the third product term? A complement and c complement. What is the fourth product term? A b c, a b c. In this way you have to design or implement programmable logic array, okay, if there is a restriction. Now we will see the same question, okay, without any restriction. Is it clear? I'm going to observe the same question, okay, same question I'm going to do same question without any restriction, without any restriction. Is it clear? If it is the same question, if you observe that the complement forms are not necessary, sorry for that. Okay, if it is same question, complement, sorry, once again, the complement forms are not necessary here. These complement forms are not necessary. Okay, need not to match here. We can simply remove this. I can able to rub this. Okay, in your programming table, need not to write it is a true form or complement form. Directly by observing this, you can able to say how many product terms are there. If you observe that how many product terms are there, okay, if you observe that how many product terms are there, 1 2 3, AC AB BC, okay, 3 product terms. Now if you observe that how many product terms here, 3 product terms, that means how many total, 6 product terms, that means 5 and 6. Okay, what are the product terms you have to write here means directly you can able to see here. I'm going to write here directly. Okay, now if you observe that what is the first product term, AC is the first product term. What is the second product term, AB is the second product term. What is the third product term, BC is the third product term. What is the fourth one, B complement C complement, if you observe this one. Now what is the fifth one, A complement C complement, and what is the finally sixth one, ABC. Okay, now in this way you have to fill this. I hope that you can able to fill this by your own. Okay, somewhat quickly I can able to fill this. If you observe that how I am going to fill this, since AC A B is not used, C AB A B C is not used, BC A is not used, BC B bar C bar A is not used, B bar C bar. Now A bar B is not used, C bar. Now A B C. Now F1, in F1 what is present? The first 3 are present in F1, the remaining 3 are not present in F1. In F2 the first 3 are not present in F2, the remaining 3 are present in F2. Okay, both are in what form? True form itself. Therefore what should you have to do? Both should be connected to 0. Here this one, then it becomes true form. It also becomes what? F2 in true form. Okay, here very important point is the first 3 are connected, the first 3 are connected to F1. Here you have to draw one more. Okay, here you have to draw 3 more gates. Okay, I hope that you can able to implement, right? Okay, now if you want I can able to draw here. If you want I can able to draw here. If you observe that, okay, I can able to draw here one more time. Okay, by keeping this programming table, if you observe that, okay, I'm going to rub this, I'm going to rub this. If you observe that I'm going to rub this. Now let's come back. If you observe that how I'm going to draw here, since 3 inputs I can able to write A complement, similarly B complement, similarly, sorry for the inconvenience guys, similarly C complement. Now how many product terms? If you observe the 6 product terms, therefore 1 2 3 4 5 6 product terms are there. Okay, now if you observe that 6 product terms are there. Okay, now therefore I have drawn 6 AND gates here. Okay, now if you observe that, how many output functions we are having? 2 output functions. This is F1, this is what, F2, and don't forget these two should be connected to an XOR gate and it should be given as 0, then it becomes F1. Okay, why? Because there is no complement form, directly we are having true form. This is F2 and this should also connected to 0. Now if you observe that the first three are connected to F1, 1 2 3. The next 3, 1 2 3 are connected to F2. Okay, 1 2 3. Okay, now if you observe that, okay, what is the first product term? A and C is the first product term. What is the second one? A and B is the second one. What is the third one? B and C is the third one. What is the fourth one? B bar C bar is the fourth one. B bar C bar. What is the fifth one? A bar C bar is the fifth one. A bar C bar. What is the last one? A B C. A B C. Okay, in this manner you can able to design PLA if there is a restriction or if there is no restriction. Okay, thank you very much for each and everyone. Have a nice day. If you are having any query, you can able to ask in the programmable logic devices. Is it clear? Thank you very much for each and everyone. Have a nice day. Okay, thank you very much.